Now this is great provided that there is only one bus master, right. There is only one device connected to the bus that is capable of changing the values of H address and control. What happens if that is not the case? That is something we have to think about, okay. And that is where the question of the bus request and bus grant signals come in, okay. So the bus request, assuming that you have multiple masters connected in a system, the bus request is something that a master can just pull high at any time, okay. So in this case, during cycle T1, some bus master asserts the request signal, okay. Now these squiggly lines over here are used to indicate that T2 may not be the next clock cycle after T1, or rather T3 may not be the next clock cycle after T2, okay. There could be any number of states in between over here before the grant signal actually comes, okay. Why might that happen? Usually because somebody else is using the bus. So even though I have requested the bus, I do not get it, I do not get the grant, but the way that the master is supposed to work is only after getting the grant signal, on the next clock edge after that, the H master signal, which is again something determined by the bus, will change to the value number 1 to indicate that bus master number 1 has now got permission. It will change to whatever number identifies that master that request that was granted permission, okay. On that same clock cycle, right, the master can now go and start putting its H address and control signals, and in the next cycle give the HW data and so on, okay. So in other words, no matter when it requested the bus, only after it has been granted the bus can it start its address and data phases. And you can see that there is further, between the request and the grant there is at least one clock cycle delay, between the grant and the master putting out the address there is another cycle delay. So if I have a situation where I am going to be continuously switching between these kinds between different masters, there is definitely going to be some loss in efficiency. So at least one thing that can be done over here, even though it may not solve the problem of what happens when I switch from one master to another, is to say a very common mode in which I want to get data from a slave is in so called burst mode, meaning that if I want to read one particular value, I then want to read the next several values, okay. This is an example of something called a burst read, right. There is a new signal over here called H trans. By the way, you do not need to worry too much about the details of these signals, I am just going through them over here to indicate how things are implemented in practice, right. But this is also specific to the AXI bus, so it is not that it is a very general, I mean, in other words, if you look at some other bus like the Avalon bus from Altera or the Wishbone bus used by OpenRISC, they will have a different set of signals. But at least conceptually you will find very similar kinds of signals in all of those, okay. So the burst transaction essentially has one extra signal over here called H trans, which is basically saying the transfer type, okay. What you can see over here is the H address again is put out by the master. There is something which indicates the burst type, okay, we will get to that in a moment, and there is also the H write and some other control signals out here, okay. H data, HW data, H ready and HR data are pretty much the same as what we were discussing earlier, right. The thing to keep in mind over here is, now let us take a slightly closer look at the addresses that we have, right. The H address that is present over here starts off with the value 0x38, okay, some address, we do not care what it is, right. And in fact the actual address, it is a 32-bit address, so it has a lot of other values which I am masking off, I am showing you only the last 8 bits over here, fine. So I put that over there. Corresponding to that, the H trans value is set to some binary value which is understood to mean non-seq. Non-seq means non-sequential, okay. The easiest way to understand that is by looking at the next value which says sequential, right, which basically means that this is the very first transaction in the burst and the next 3 transactions are sequential increments of the starting address. Okay. How do I know the next 3? Because this burst, the H burst value is set to a 4 burst wrapping sequence. Okay. What does a 4 burst wrapping sequence mean? Look at the addresses. It is first 0x38, the next address is 0x3c, which if you do the math in hexadecimal is this 38 plus 4. Now 3c plus 4 should have gone to 40, right, but what we say is instead it wraps around, okay, and it wraps around on a boundary of 16. In other words, only this bottom value over here, the c, gets set to 0. Okay. So the next value becomes 0x30, next one after that is that plus 4, so 0x34. Okay. There are other ways. Instead of wrap 4, I could just do increment 4, which means it would just increment 4 times. Okay. So all of these, why are these different kinds of bursts introduced? Because people have found that they are often useful in different kinds of code. Okay. It turns out that if you have a wrapping burst, then there are certain kinds of codes that can be automatically optimized for that. If you have a for loop which is perpetually reading through one array, let us say you are doing a filter, right, at the end of going through all the coefficients you have to wrap back to 0 and start again, right. A burst read of that sort is probably useful in such a context. So burst reads, even though they cannot get over the entire handshaking overhead, will still allow you to sort of say, okay, you know, I can go through this entire process of, I can automatically push some of the complexity if necessary into the slave logic and thereby ensure that certain kinds of transactions are done in a slightly more compact and efficient way. This is a busy slide, but effectively all that you need to focus on is H grant M1 and H grant M2, right. What does that mean? One is going from 1 to 0 and the other is going from 0 to 1. The arbiter has switched ownership of the bus from M1 to M2 at some point in time. Okay. But look at what is happening over here. If I look at the duration corresponding to master 1, at the time T3 when the transition was made from M1 to M2, it was still in the middle of a burst. Okay. So what happens? Do I have to immediately drop everything and switch over? No. The bus basically allows that master M1 to continue until it finishes that burst, and then ownership in cycle number T5 switches over to master number 2, which can then go ahead and start putting out its address and control signals and so on. Okay. In between you can see that the H ready is going through a number of up down phases. That is what is basically stretching out these transactions to 2 cycles each and so on, right. But the point is, the bus protocol by itself is defined at a sufficiently abstract level that you really do not care how many cycles are there between each of these operations. That is the power of the protocol, right. All that it says is it specifies the meaning of each of these different kinds of signals, and by appropriately using the signals you can get pretty much any kind of handshaking functionality that you want. Okay. So this essentially is used to illustrate that, you know, how would I transfer ownership of the bus. The arbiter would change the grant signal from M1 to M2. M1 still has time to finish its burst, but as soon as it has finished that particular burst, it can't start another burst, it can't start any further transaction because ownership has been switched over to M2 at that point. Now all of this was using something called the AMBA bus, right, which was version 2.0 of the ARM microcontroller bus. In version 3, they introduced a slightly modified variant of this, right. Essentially they found that there were, based on their analysis of how people were using the protocol in version 2, they came up with some enhancements. One of them was they essentially proposed this concept of channels for reading and writing. Okay. So what, from here onwards what we are looking at is something called the AXI bus. It refers more to the AXI bus, which is after all a variant of the AMBA bus. Okay. In the AXI bus, the read address channel essentially says that it is a master interface, just gives out address and control. It is just given once, I do not have to give addresses for every single read value. The slave will then respond with a series of read data. Okay. One way to look at to understand this is effectively every transaction now is considered a burst. You can change the length of the burst to anything you want, right, within certain limits, but every transaction will just have one address and control signal going out corresponding to it. You can think of that as the address channel which is used to communicate that information to the slave, and the slave then responds on the read data channel with possibly multiple data coming back. What happens in the case of writing? Once again, only one address and control followed by multiple write data going out on the write data channel. Okay. Now there is something called the write response channel, right. There has to be handshaking. The slave has to somehow get back saying yes, I accepted this. It could be something as simple as the H ready signal, or there could be something a little bit more complicated to tell the master what is being responded to, right. And thinking of this write response channel as something that can convey more information than just the ready signal actually allows us to bring in one additional level of control, right, which we will see later. That additional level of control is essentially something called the AXI ID, the transaction ID identifier. Okay. So effectively what happens is, let us say that we are talking about a write transaction, right. Along with all the other signals, the address, size, valid, ready and so on, there is also a signal called AWID. Okay. And that AWID is essentially saying this is the ID used for the write transaction. As you can see over here, that is essentially going 0, 1, 2, it is just incrementing. Okay. So why should I bring in something of that sort? What is the purpose of bringing in an ID associated with every write transaction? It looks as though all that I have done is add a few more signals to my bus. Okay. This becomes crucially useful when we look at what can happen if I had a system that had one very slow slave. Okay. So what would happen in the AMBA AHB bus is that I would need to give out addresses like this, right. Let us say that I wanted to do a 4 burst read followed by another 2 burst read and a 2 burst read, right. So the addresses corresponding to that would be A11, A12, A13, A14, that is the first burst. A21, A22 would be the second, A31, A32 would be the third and so on, right. Now let us say that A11 is basically going out to a peripheral that is very slow to respond, has a high latency. Okay. What will end up happening is A11, A12, A13, A14 are put out on the bus, the slave immediately makes ready low, you just have to wait until the data from that slave comes back, and D11 is coming back out here, D12 is here, D13 is here, it is basically going off the edge of the page, right. So I can't even like show you when D21 is going to come back. Okay. But the only thing that is clear is D21 can only come back after all of these have finished. But what if D21 corresponded to a fast peripheral, let us say the on chip RAM, right, then this is an unnecessary waste of resources. AXI, the first thing is everything is now a burst transfer. Therefore, I do not need to do this A11, A12, A13, A14, I do not need to give out 4 addresses, just that one clock cycle giving the A11 and the burst length was sufficient, right. The second thing is, because I now have transaction IDs, I can think of doing things out of order. Okay. So A11 goes, the bus is not able to respond to that immediately, or rather the slave is not able to respond. That does not matter, I can still go to A21. Now this could be from the same master, it need not be that I am actually switching masters over here, because if I wanted to switch masters I would still need to go through the bus request grant, all of that, but in principle even that can be possible, I will probably add a couple of cycles over here, that is all. But even if it is with the same master might issue the next bus request, A21. Now the interesting thing is, let us say that A21 is coming back fast, I straight away get the data D21, and D22, that burst happens successfully. Okay. I can then go further. I could have given A31 over here, or maybe I just wait and give A31 after another cycle, it does not matter when, right. Let us say that A31 also comes back, it has some more latency than 2, but on the other hand still comes back a couple of cycles later, right. But all the data is now available, and A11 only now has finally got the data ready, and D11 is able to come back, right. What would happen if operation 3 was pushed still one cycle further, D31 and D32 over here? That is okay. Once I have granted the permission to this particular transaction to go ahead, that transaction completes, and only then the D11, D12 etc. can start. Okay. So obviously I am glossing over a lot of details over here, but in principle at least you can see how this can be made to happen. The moment I associate the transaction ID with every transaction, it means that the arbiter, the master, as long as they all understand mutually what is going on, it is possible to essentially switch over from one transaction to another and say I will wait until that let other transactions go ahead and wait until this transaction has time to complete. Okay. So with that I am going to stop the discussion of the bus protocols. Hopefully this is enough to give you an idea of what kind of complexity goes into a bus, right. It is not just a set of 3 wires, right. There is a lot more to it. All that complexity essentially goes into the design of the arbiter as well as some of the other handshaking logic built around it. Okay. There are many different buses used in many kinds of computer systems. The AXI bus is the one that is typically used for ARM based system nowadays, but is also taking off in a big way for most other microcontrollers and microprocessors, for a lot of others, I think including the RISC-V system that is becoming very popular now. Okay. But if you look at the Intel x86 for example, that has a different bus structure, the MIPS, the Sun Spark, many of those kinds of things usually have, many of them have different types of bus structures of their own, but the complexity wise they are all going to be similar and the capability wise.